Let's now talk about some techniques for solving systems of differential equations. So suppose we have the system of differential equations given here. X1 prime is 4x1 minus 3x2, and x2 prime is 6x1 minus 7x2. So this is a system of first-order differential equations. And note that we can't use our usual techniques by separating variables or trying to use a general first-order solution. It's just not going to work. This is a wholly different set of differential equations. And we say they're coupled together in this way. So the technique that we're going to use is to write our differential equation in matrix form. And so the way we do that is we write it as a matrix product. So we write this differential equation as x vector prime is equal to some matrix times x vector, where x vector is x1, x2, and x vector prime is x1 prime, x2 prime. Okay, and so you see that the entry of the matrix are the entries of our differential equation. Usually we write this as x vector prime is equal to ax vector, where A is this particular matrix. So another example of that is x prime is equal to 4x plus 2y, and y prime is 3x minus y. So you can write this in a matrix form as x prime is this matrix times x, where now x is the column vector of x and y. Okay, and so the way we solve these systems is actually using a technique we already learned from matrices. We use the technique of eigenvalues and eigenvectors. So let's see how they apply to solving first-order differential equations that are coupled. So let's take the example we had above. X prime is equal to ax, where A was the matrix 4, negative 3, 6, and 7. And so one way to solve this is to make a guess. And that's usually what we do in our second-order systems of differential equations. We make a good guess. So let's make the guess that x is equal to x naught, which is some constant vector, times e to the lambda t for some lambda. And as with second-order systems, what we need to do is figure out what lambda is. So we plug this into our differential equation, and it becomes lambda x naught e to the lambda t is equal to a x naught e to the lambda t. We can cancel out the e to the lambda t's, but not the x naught vectors. And we get the matrix equation ax naught is equal to lambda x naught. This should look really familiar. This is actually the equation for an eigenvalue of the matrix. That's what we define to be an eigenvalue of the matrix. So let's solve this equation for the eigenvalues lambda, which is after all why we called it lambda. So if you recall, when we solve for eigenvalues, we write this in the form a minus lambda times the identity matrix times x naught is equal to 0, or the determinant of a minus lambda I is equal to 0. Writing that out, we get a matrix that looks like this, and taking its determinant, we get some expression that we can simplify, and simplified it looks like lambda squared plus 3 lambda minus 10 is equal to 0. The solutions to this equation are lambda equal to negative 5 and lambda equal to 2, and so those are the eigenvalues of our matrix A. So now we're going to solve for the eigenvectors, now that we know the eigenvalues. And so if you recall, what we need to do to solve for eigenvectors is we need to solve the equation A minus lambda times the identity matrix times x naught is equal to 0 for our eigenvectors x naught. For lambda equal to negative 5, we get an expression that looks like this. And so we get two equations for the components of x naught, our eigenvector. Both of them are equivalent. And so one solution to this is x1 is 1/3 x2. Or if we choose the simple solution, the eigenvector for lambda equal to negative 5 is just the column vector 1, 3. For lambda equal to 2, we do a similar thing. We write the matrix A minus lambda I and solve this equation for x1 and x2. Again, the two equations are degenerate, so we just find one solution where x1 is, say, 3/2 x2. And so our second eigenvector is the column vector 3, 2. That's the eigenvector for lambda equal to 2. Then the general solution is just the sum of these two eigenvectors with the eigenvalue solutions that we had before. So x vector c1 e to the minus 5t times its eigenvector, c2 e to the 2t times its eigenvector. Using the eigenvectors we have above, we can write this in a little bit more of a transparent notation in terms of the column vectors. But it's still not particularly clear. Let's write that in terms of the original variables x1 and x2. And so our general solutions are c1 e to the minus 5t plus 3c2 e to the 2t for x1, and for x2, 3c1 e to the minus 5t and 2c2 e to the 2t. Notice we had two unknown constants in this final solution, and that makes sense because we had two first-order differential equations. So we should have two unknown constants. Okay, let's look at another example just to see how this works again. So consider the differential equations x prime is equal to 4x plus 2y, and y prime is equal to 3x minus y. So in matrix form, it looks like x prime is equal to ax, where a is this matrix. So we let x be e to the lambda t times x naught for some constant eigenvector x naught. And we end up with an eigenvalue equation for the eigenvalues of a. So a minus lambda I times x naught must be equal to 0. So again, we'll find our eigenvalues by finding when the determinant of a minus lambda times I, the identity matrix, is equal to 0. And so we get some expression that looks something like this. You take the determinant, and this simplifies to something that looks like lambda squared minus 3 lambda minus 10 is equal to 0, kind of similar to our previous example. And so the eigenvalues are -2 and 5. Now to find the eigenvectors, we go eigenvalue by eigenvalue to figure out what these eigenvectors are. And recall, we're trying to solve this equation a minus lambda times the identity matrix times the eigenvector x naught is equal to 0. So what this turns into for our eigenvalues, or in our eigenvectors, are two equations which can be solved by y is equal to minus 3x. We're choosing the simple solution. We get a column vector for the eigenvector for lambda equal to -2 of 1 and -3. For lambda equal to and lambda equal to positive 5, the other eigenvalue, you get similar looking expressions. You get two equations which are degenerate with each other and can be solved by x is equal to 2y. And so the eigenvector here should be 2, 1, and that's the eigenvector for lambda equal to 5. Therefore, the general solution is the sum of those eigenvectors with e to the lambda t for the eigenvalues associated with them. So we get that the x vector is equal to c1 e to the minus 2t times the first eigenvalue, c2 e to the 5t times the second eigenvector. Or you could write this out again in terms of the actual column vectors for the eigenvectors. Or what actually makes more sense is writing it in terms of x and y, our original coordinates. So c1 e to the minus 2t plus 2c2 e to the 5t for x, and for y, minus 3c1 e to the minus 2t plus c2 e to the 5t.